We as humans need a lot of energy, and the photons are arriving on this Earth all the time. So we just have to figure out a way to get the energy from photons into a useful form. Solar panels have become the leading form of the utilization of solar power. Solar panels are made from silicon that's formed into ingots, then sliced into wafers, and then cells are created, which we will learn a lot more about later. Here's some additional reasons why solar energy is good. It's renewable, it's abundant, it's very helpful with regards to carbon dioxide emissions, and it's become economically viable. It's become the cheapest source of energy, even including the use of batteries. Silicon itself is thermally stable, durable, and easy to process. There's three major silicon solar cell materials out there at the moment. There's thin film, monocrystalline, and polycrystalline. Polycrystalline materials are formed by melting together smaller crystals in a jumble, and then the wafers are sliced out of that. More of the older solar panels were polycrystalline. The newer method is to create a monocrystalline material and slice the wafers out of that. The wafers themselves are made out of two semiconductors bonded together, P-type silicon and N-type silicon. You need these two types in order to drive electrical energy, which we will learn about next. The P-type semiconductor has some atoms such as boron or gallium with one less electron in the outer energy level than silicon. Because boron has one less electron than is required to form the bonds with the surrounding silicon atoms, an electron vacancy or hole is created. In N-type semiconductors, there's an atom such as phosphorus that has one more electron in its outer energy level than silicon does. Because phosphorus has this one more electron than is required to form the bonds with the surrounding atoms, its unbonded electron is free to move. But if we look at this solar wafer cross-section, we see that the N-type semiconductor is placed above the P-type semiconductor. And this is where things really start to happen. At the contact surface, the electrons leave the N-type layer and flow into the holes in the P-type layer. This is called the depletion zone. Look at the left side on the following figure. When a photon hits an electron loose from the silicon depletion zone, a loose electron flows up into the N-type layer and a hole moves down into the P-type layer. If we connect a metal wire to the two sides, electron flow is induced in the wire that can be used by electrical devices or connected to the grid. Look at the right on the following figure. In the lower right, you'll see a photon, which is the wavy yellow line, coming in and striking loose an electron. Then the electron streaks upward into the N layer, and the hole left by the departure of that electron goes down into the P layer. And the difference between these two distances, where the hole ends up and the electron ends up, is the electrical potential. This electrical potential drives a current, a DC current, direct current, that flows through the wires at the back of the illustration, where you see the light bulb is being lit by the energy produced by the photons. But most appliances and devices use alternating current, or AC abbreviated. Inverters are used to change the DC to AC to power local devices or to allow interconnection with the grid. How do inverters change DC to AC? Well, they switch the direction of a DC input back and forth very rapidly. What else do inverters need to do? They need to match the frequency and timing of the cycles in the grid. Here we have some examples of inverter outputs. The simplest one is a square wave designed to match the sine waves in the grid. Not very efficient. They improved on that and formed modified square waves, as illustrated in the middle of that diagram. And then with a little work with computers and so forth, they have made pretty much pure sine waves that match the sine waves of the grid. You may have wondered where the AC current from the inverter is connected to the system such that it integrates with the grid. Well, the connections can be one of two ways. Load side connection made after the main breaker, or a line or supply side connection made before the main breaker. The load side is the most common. Here's some schematic diagrams showing you the two types of interconnection that can happen. Let's look at the load side first. These parentheses items, that's actually the main breaker, and here's the meter going out to the grid. The connection coming from the inverter is below the main breaker, and the green is grounding. If we switch over to the line or supply side connections, we see the inverter is just below the meter in that picture and above the breaker box and above the main disconnect. Also, please note that neither diagram shows the DC power coming into the inverter. That, of course, is necessary. The foregoing is a lot about how solar panels work, and a little bit about how they're assembled and put together. I hope you've enjoyed this. Next, I'll show a link to a very helpful government-produced document that provides a lot of further information about how to put together a solar system to be compliant with codes and all the necessary requirements. Rather than typing in that long link to your web browser, you might find it easier to perform a web search for that title, Solar PV permitting and inspecting, and use the site that comes up on the NYSERDA website. NYSERDA is the New York State Energy Research and Development Authority. I hope you've enjoyed learning about photovoltaic systems, and I hope that this information will be useful to you, whatever your degree of involvement in the future. Good luck.